Hello, I'm Guo Keshan. Today I'm going to present my topic, open sets. The focus of this presentation is a definition of open sets using open balls. I will first introduce the background and definitions, then present a rigorous proof showing that every open ball is an open set. Finally, I will give some examples, discuss an application, and conclude the presentation. Before defining open sets, let us first understand why we need this concept. In elementary calculus, we often work with intervals such as an open interval AB. These intervals seem simple, but they already contain the essential idea of openness. When we move from one dimension to higher dimensional spaces, intervals are no longer sufficient, so we need a more general concept. This motivates the introduction of open balls. In real analysis, we often want to distinguish points that are truly inside a set from those that are close to its boundary. Intuitively, if we stand at an interior point, we should be able to move a small distance in any direction without leaving the set. This intuitive idea is described mathematically using the concept of a neighborhood. In Euclidean space Rn, neighborhoods are represented by open balls. Therefore, open balls naturally lead to the definition of open sets. We begin with the definition of an open ball. In one dimension, an open interval can be viewed as all points within a certain distance from a center point. We generalize this idea to higher dimensions. Given a center x0 and a positive radius r, the open ball consists of all points whose distance from the center is less than r. Notice that the boundary is not included because the inequality is strict. This is exactly why we call it an open ball. If we change the inequality to less than or equal to, we would obtain a closed ball instead. You can think of an open ball as a higher dimensional version of an open interval. Now we are ready to define an open set. A set is called open if every point inside the set has an open ball centered at that point that is completely contained within the set. Notice that the radius does not have to be the same for every point. Different points may have different radius. The important idea is that every point has some room around it without leaving the set. Another important point is that radius does not have to be the same for every point. Points near the center may have a large neighborhood, while points close to the boundary may require a much smaller one. As long as such a positive radius exists, the definition is satisfied. So before presenting the proof, let's first look at this geometric illustration. The picture provides the geometric intuition behind the proof. Instead of trying to prove the statement immediately, we first ask ourselves how large the smaller ball should be. Since the point x is already inside the original ball, there is some remaining distance to the boundary. We simply using this remaining distance as a new radius. The key idea is that this smaller ball centered at x stays completely inside the original ball. So now let's prove that every open ball is an open set. Let S be an open ball centered at x0. We choose an arbitrary point x inside S. Choosing an arbitrary point is a common technique in mathematical proofs, because if we can show the property holds for any point, then it holds for the entire set. Since x belongs to the ball, its distance to the center is less than the radius. We then define a new radius r1 as the difference between the original radius and the distance from x to the center. Because this difference is positive, the smaller ball exists. Our goal is to prove that this smaller ball is completely contained in the original ball. Now let y be any point inside the smaller ball. Using the triangle inequality, we obtained an upper bound for the distance between y and the original center x0. After substituting the definition of R1, we find that this distance is still smaller than the original radius. Therefore, Y also belongs to the original open ball. Since every point in a smaller ball remains inside the original ball, we conclude that the smaller ball is contained in the original ball. This proves that every open ball satisfies the definition of an open set. Now let's look at a simple example. Consider the open interval AB. For any point inside the interval, we choose the radius as the minimum distance to the two endpoints. This guarantees that the neighborhood remains entirely inside the interval. Therefore, every point satisfies this definition of an open set. So interval AB is open. Now let's also consider a set that is not open. Take the closed interval 0, 1. Notice that the problem is not the points inside the interval. Every interior point satisfies the definition. The only issue is that the boundary point, since the definition requires every point to satisfy the condition. One counterexample is enough to conclude that the set is not open. Look at the endpoint 0. No matter how small the radius is, an open ball centered at 0 always extends to the left of 0. Therefore, the neighborhood cannot be completely contained in the interval, since even one point falls the definition. The set 0, 1 is not an open set. Now let's look at the application. Open sets are not only definitions, they are also fundamental in many areas of analysis. One important application is the definition of continuity, as we learned in class. In elementary calculus, continuity is usually introduced using the epsilon delta definition. This definition describes how small changes in the input affect the output of a function. In real analysis, we learn another equivalent way to define continuity. Instead of using epsilon and delta directly, we say that a function is continuous if the pre-image of every open set is open. Although these two definitions look quite different, they describe exactly the same concept. The open set definition is often more elegant and more suitable for higher dimensional spaces and more advanced mathematics. Therefore, open sets are not only an important topic by themselves, but also provide the foundation for studying continuity and many other concepts in real analysis. To conclude, we first introduced open balls and used them to define open sets. We then provide that every open ball is itself an open set. Finally, we looked at examples and discussed an important application. Open sets are one of the most fundamental concepts in real analysis and form the basis for many later topics. And that's all for my topics. Thank you for listening. 给你吹吧，应该可以。